Welcome. Today we're diving deep into all things concrete, using as our guide the Concrete Handbook. We'll be breaking it down and dispelling some common myths and exploring the fascinating world of, well, its production and applications. You might be surprised to learn that concrete is far more than just a simple mixture. It's a material that's shaped our civilization and is still evolving today to meet modern challenges like, especially, sustainability. So before we get into it, I'll quickly welcome. Today we're diving deep into all things concrete, using as our guide the Sitka Concrete Handbook. We'll be breaking it down and dispelling some common myths and exploring the fascinating world of, well, its production and applications. You might be surprised to learn that concrete is far more than just a simple mixture. It's a material that's shaped our civilization and is still evolving today to meet modern challenges like, especially, sustainability. So before we get into it, I'll quickly run through what we'll cover. We'll start with why concrete's more than just a mixture, then explore the environmental impact of its production and how the industry is, striving for sustainability. And finally, we'll delve into the five key components that make up concrete: cement, water, aggregates, admixtures, and their crucial roles in shaping that final product. So let's start by busting that myth that concrete is just a simple mix. The Sitka Concrete Handbook reveals that concrete is actually a complex matrix of 5 key components.
It's this intricate interplay between cement, water, aggregates, things like sand and gravel, and admixtures that gives concrete its amazing versatility, from towering skyscrapers and massive bridges to even sidewalks and intricate architectural facades. This material really does shape our built environment, but with such widespread use, comes a responsibility to address its environmental impact. And the handbook sheds light on this by going into the carbon footprint that's associated with cement manufacturing, a significant concern given the sheer volume of concrete used globally. This leads us to a crucial question: how can something as seemingly simple as concrete be sustainable? Well, the Sitka Concrete Handbook actually offers several answers. It highlights the growing need for sustainable practices in the industry and gives insights into how we can actually achieve this. One of the key strategies that's discussed is the use of concrete admixtures. These admixtures can play a critical role in reducing the cement and water content needed in concrete mixes, which leads to lower carbon dioxide emissions. For example, the handbook highlights the use of superplasticizers in the construction of a massive ethylene concrete buffer tank in Belgium. By reducing the water and cement content, these admixtures really significantly lower the environmental footprint of the project. Another approach discussed is the concept of life cycle assessment. This method evaluates the environmental impact of concrete throughout its entire lifespan, from the initial raw material extraction all the way to its disposal. By understanding the full picture, LCA guides us toward more sustainable practices, encouraging us to consider the long-term consequences of our material choices. Besides superplasticizers, the handbook also talks about using other admixtures to improve sustainability. One example is admixtures that actually allow the use of recycled aggregates. And this is really relevant in a world where conserving resources and minimizing waste are top priorities. A compelling example from the handbook is the construction of a sports stadium in Zurich using recycled aggregates from excavated material. This project really significantly reduced raw material extraction and transportation pollution and demonstrated the potential of circular economy principles in concrete construction. Now let's shift our focus to the 5 pillars of concrete, the components themselves. The handbook breaks down each component in detail, starting with cement. Cement, often called the glue that holds concrete together, comes in different types, each with its unique properties. The most common type, Portland cement, involves a really fascinating production process, heating a mixture of limestone, clay, and other materials to incredibly high temperatures. Now, while this process is energy intensive and contributes to cement's high carbon footprint, the handbook does provide valuable insights into how the industry is working to reduce this impact. Moving on to water, we learned that it's not just a mixing agent, but also a factor that significantly influences concrete properties.
The handbook really emphasizes that water quality is key, discussing the suitability of various water sources and highlighting potential problems with impurities that can affect the concrete's performance. You might be surprised to know that seawater can be used for non-reinforced concrete. However, due to its high chloride content, it's not suitable for reinforced or pre-stressed concrete. This just goes to show how even seemingly simple components like water, require careful consideration in concrete production. Next up are aggregates, which make up the bulk of the concrete's volume. The handbook delves into the different types of aggregates, both fine and coarse, natural and recycled, explaining how they impact the concrete's strength, workability, and even its aesthetics. Aggregates can be thought of as kind of the skeleton of concrete, providing structural integrity and influencing the final texture and appearance. Finally, we get to admixtures, which are often described as the magic ingredients that, fine-tune concrete properties.
Yeah.
Admixtures are really versatile. They can reduce water content, control setting time, entrain air, and even enhance durability. The handbook provides a comprehensive overview of these admixtures and their wide range of functions, emphasizing how they contribute to both performance and sustainability. The handbook also stresses the importance of mixed design, where the proportions of all these components from cement to admixtures are carefully balanced. This delicate balancing act is critical for achieving those specific performance requirements for different applications. Whether it's a high-rise building or a simple sidewalk, mixed design ensures that final product meets the demands of the project. So having examined the individual components, let's transition from those static ingredients to the dynamic properties of fresh concrete. The handbook really emphasizes that fresh concrete is a living material constantly evolving, before it hardens. This dynamic nature makes it both challenging and fascinating to work with. The handbook dives into key properties like workability, setting time, air content, and the phenomena of bleeding and segregation, explaining how these factors can influence that final concrete quality. Workability, which refers to how easily fresh concrete can be placed, compacted, and finished, comes in different consistence classes, measured by tests like the slump test. This test measures the concrete's ability to flow, ensuring that it can be properly placed and finished. Setting time is another critical property. It determines how quickly the concrete begins to harden. The handbook explores those factors that influence setting time and how admixtures like retarders and accelerators can be used to actually control this process, allowing for flexibility in construction schedules. Air content is particularly important in regions with freeze-thaw cycles. Through air entrainment, achieved by using specific admixtures, tiny air bubbles are created within the concrete. These bubbles actually act as miniature chambers, providing space for the water to expand when it freezes, preventing damage to the concrete structure. The handbook also addresses two challenges that can occur in fresh concrete: bleeding and segregation. Bleeding is the tendency of water to rise to the surface, while segregation describes the separation of aggregates from the cement paste. Both phenomena can compromise the concrete quality, but the handbook provides insights into how they can be minimized through proper mixed design and handling techniques. As you can see, even in its fresh state, before it even begins to harden, concrete presents a multitude of factors to consider, each playing a crucial role in that final product's quality and performance. Now, let's turn our attention to the various methods of concrete application, each tailored to specific project requirements and construction scenarios. The handbook offers a fascinating overview of these methods, starting with a traditional crane and bucket approach. Crane and bucket, while simple and versatile for placing a wide range of concrete types, has limitations in terms of the volume placed in a given time. The handbook then discusses pumped concrete. This is ideal for large-scale projects and high placement rates. It emphasizes the importance of a suitable mixed design for pumpability as the concrete needs to flow smoothly through the pump lines without segregating or blocking those pipes. Pumped concrete has really revolutionized modern construction, allowing efficient placement even in the most challenging locations. Moving on from traditional methods, the handbook introduces self-compacting concrete, or SCC, an innovative solution for complex geometries and congested reinforcement. SCC flows effortlessly into place, even in tight spaces with minimal need for vibration. This reduces labor and noise, making it ideal for urban environments and intricate designs. The handbook highlights SCC's unique flow properties and advantages for achieving those high-quality finishes with reduced effort. SCC truly showcases the continuous innovation happening in concrete technology. The handbook also explores sprayed concrete. This is often used for tunnel linings and slope stabilization. It explains how sprayed concrete can be applied directly onto surfaces without formwork, a highly flexible and efficient method showcasing concrete's adaptability to those diverse construction environments. Sprayed concrete can even be used for underwater applications. Finally, the handbook discusses precast concrete. This is where elements are cast in a controlled factory setting before being transported to the construction site. Precast concrete offers advantages like faster construction times and improved quality control as elements are produced in dedicated environments with optimal curing conditions. The handbook explains the different types of precast elements and emphasizes efficient curing methods for achieving the desired strength and durability. Now that we've explored the dynamic world of fresh concrete and its diverse application methods, let's transition to the properties of hardened concrete. We'll be exploring how it gains strength and durability over time through the fascinating process of hydration. Hydration, the chemical reaction between cement and water, is the key to concrete's transformation from a fluid paste to a solid, durable material. The handbook breaks down the key properties of hardened concrete, starting with compressive strength. It's the concrete's ability to resist crushing under load. Compressive strength is really fundamental to the concrete's structural integrity. The handbook discusses those factors that influence compressive strength, such as the water to cement ratio, the type of cement used, and the curing conditions. It explains how compressive strength is determined using standardized tests where cylindrical or cubic specimens are subjected to increasing pressure until failure. Next, the handbook moves on to flexural strength.
This is concrete's ability to resist bending or cracking under load. Flexural strength is especially important for structural elements like beams and slabs that are subjected to bending forces. The handbook explains how this property is tested, usually by applying a load at the center of a beam specimen until it breaks. The handbook also introduces Young's modulus of elasticity, or the E modulus, which represents concrete stiffness and resistance to deformation under load. This property is crucial for understanding how concrete will behave under stress and for designing structures to withstand those anticipated loads. The E modulus essentially measures how much concrete will stretch or compress under a given force. It's a key factor in structural engineering calculations. Finally, the handbook dives into durability. This encompasses a range of properties that determine how well concrete will withstand environmental conditions and resist deterioration over time.
Durability ensures that concrete stands the test of time, from harsh weather to chemical exposure and everyday wear and tear. The handbook discusses various aspects of durability, including water tightness, frost resistance, sulfate resistance, and abrasion resistance, emphasizing how proper mix design, construction practices, and curing methods contribute to a durable and long-lasting structure. Now let's take a closer look at watertight concrete construction. The handbook introduces the white box concept, a comprehensive approach to building watertight structures that goes beyond simply using a waterproof concrete mix design. The white box concept emphasizes carefully designed joints to accommodate concrete shrinkage and movement, preventing cracks that could allow water to get in. It also highlights the need for proper concrete placement techniques to ensure a homogeneous and compact structure, minimizing the risk of voids and leaks. In essence, the white box concept is a holistic approach, considering every aspect of construction to ensure a truly watertight structure. Next, the handbook provides practical guidance on various aspects of concrete construction, sharing insights gleaned from years of experience and expertise. It starts with formwork and release agents, discussing their selection and use to ensure clean and defect-free concrete surfaces. Formwork provides that temporary mold for shaping the concrete, while release agents prevent the concrete from sticking to the formwork, allowing for easy removal. The handbook emphasizes choosing appropriate materials for both formwork and release agents, considering factors like the type of concrete, the desired finish, and the environmental conditions. The handbook also provides practical tips for concrete installation, emphasizing proper pouring techniques, vibration, and finishing to achieve the desired concrete quality and appearance. Proper vibration ensures that the concrete's adequately compacted, eliminating air pockets and achieving a dense and durable structure. Finishing techniques like troweling or brushing, create that desired surface texture and appearance. Finally, the handbook provides detailed recommendations on curing methods and durations. Curing is a crucial step involving maintaining adequate moisture and temperature for fresh concrete to allow for that optimal hydration and strength development. The handbook explains different curing methods, such as covering the concrete with plastic sheeting, applying curing compounds, or misting with water. It emphasizes the importance of protecting fresh concrete from premature drying and temperature extremes to prevent cracking, reduce strength, and diminished durability. Proper curing is essential for maximizing concrete strength and durability, ensuring it withstands the test of time and performs as intended. It's amazing how much attention to detail is required at every stage of concrete production, from selecting the right materials to the final curing process. And the Sitka Concrete Handbook does a fantastic job highlighting the key considerations and best practices for achieving that high quality durable concrete. Now let's delve into some specific types of concrete, each tailored to meet particular performance requirements. The handbook provides insights into various concrete types, starting with waterproof concrete, essential for structures like basements and underground tanks. Waterproof concrete prevents water from penetrating the structure, protecting it from moisture damage and maintaining its integrity. The handbook explains that achieving waterproof concrete involves a combination of factors: a low water to binder ratio, using pore blocking admixtures, and meticulous attention to detail during construction. It also emphasizes the importance of a well-graded aggregate mix and thorough compaction to minimize voids and ensure a dense, impermeable concrete matrix. The handbook then revisits pumped concrete, which is often used for those large-scale projects and high placement rates. It highlights the importance of a cohesive mix design for pumpability, ensuring that the concrete can flow smoothly through pump lines without segregating or blocking the pipes. The mix design must be tailored to the specific demands of the pumping process, balancing flowability with stability to prevent segregation and ensure efficient placement. The handbook also provides guidance on selecting appropriate pumping equipment and techniques, emphasizing the need for skilled operators who understand the nuances of pumped concrete. Now, let's turn our attention to self-compacting concrete, or SCC, which has revolutionized concrete construction in so many ways. The handbook explains how SCC's unique flow properties allow it to fill complex formwork and congested reinforcement without vibration. This not only simplifies construction, but also reduces labor costs, noise pollution, and vibration related damage. The handbook delves into the mix design principles for SEC, emphasizing the importance of achieving a high degree of stability to prevent segregation and ensure a homogeneous concrete structure. It also discusses various testing methods used to evaluate the flowability and stability of SCC, ensuring that it meets performance requirements. Next, the handbook covers sprayed concrete, often used for applications like tunnel linings and slope stabilization. The handbook explains how sprayed concrete is applied using a high velocity stream of air, which propels a mixture of cement, aggregates, and water onto the surface. This method allows a rapid placement of concrete in those challenging environments, even on vertical or overhead surfaces. The handbook delves into the different types of sprayed concrete, including dry mix and wet mix processes, highlighting the advantages and limitations of each approach. It also provides guidance on selecting appropriate equipment, nozzle techniques, and safety precautions for sprayed concrete applications. Now let's explore precast concrete, where elements are cast in a controlled factory setting and transported to the construction site. Precast concrete offers advantages like faster construction times and improved quality control, because elements can be produced in dedicated environments with optimal curing conditions. The handbook explains the different types of precast elements and emphasizes the importance of careful handling and transportation to prevent damage and ensure their integrity upon arrival at the construction site.
It also stresses the need for proper connection details between precast elements to ensure that they function as a cohesive structural system. Having explored these fundamental concrete types, we can move on to some more specialized types, each with its unique properties and applications. We'll begin by looking at fiber reinforced concrete, which incorporates fibers into the mix to enhance its properties.
Fibers, which can be made from materials like steel, glass, or even synthetic polymers, add strength, strength, ductility, and toughness to concrete. Think of them as like tiny reinforcing elements within the concrete matrix, distributing stresses and preventing those large cracks from forming.
That's a great analogy. So instead of one big crack forming, the fibers help create a network of smaller, less impactful cracks.
Exactly. The handbook explains the different types of fibers and their specific benefits, highlighting how they improve the concrete's resistance to cracking, impact, and abrasion. It also discusses the mixed design considerations for fiber-reinforced concrete, emphasizing the importance of achieving that proper fiber dispersion and orientation to really maximize their effectiveness.
So it sounds like fiber-reinforced concrete is kind of like adding a safety net to the concrete mix, making it more robust and resilient to damage.
That's a good way to put it. Now, let's move on to high-strength concrete, which, as its name suggests, exhibits exceptional compressive strength.
I imagine this type of concrete is used in structures that need to withstand those immense loads like skyscrapers or bridges.
You're absolutely right. High-strength concrete is often used in high-rise buildings, bridges, and other structures that demand that exceptional load-bearing capacity. The handbook explains how achieving high strength involves a combination of factors, including a low water to cement ratio, the use of high strength aggregates, and careful curing practices. It also highlights the role of admixtures such as superplasticizers and silica fume in enhancing the strength and durability of high strength concrete.
So it's not just about using stronger ingredients, but also about optimizing the mix design and curing process to really maximize the concrete's potential.
Precisely. Now, shifting gears a bit, let's talk about lightweight concrete, which is often used for applications where weight reduction is a primary concern.
I'm curious, how do you make concrete lighter without compromising its strength?
That's a great question. The secret lies in using lightweight aggregates such as expanded clay, shale, or slate. These aggregates have a porous structure that reduces the overall density of the concrete while still providing adequate strength for many applications. The handbook discusses the different types of lightweight aggregates and their properties, highlighting their benefits for reducing dead loads in structures, improving thermal insulation, and enhancing fire resistance.
Cool. So it's like using puffed rice instead of regular rice in a recipe. You get a similar volume, but with less weight.
That's an excellent way to think about it. It's amazing how lightweight concrete can provide both structural and functional advantages, making it a versatile choice for various construction needs.
Now, let's dive into a type of concrete that seems almost counterintuitive, underwater concrete. How do you even pour concrete underwater?
Underwater concrete, used for structures like bridge piers, foundations, and marine structures, presents unique challenges that the concrete mix needs to be designed to prevent washout and segregation as it's placed in that fluid environment. The handbook explains the special considerations for underwater concrete mix design, including the use of high cement contents, anti-washout admixtures, and careful placement techniques. It also highlights the importance of monitoring the concrete's properties and ensuring adequate curing in an underwater environment.
It sounds like underwater concrete construction requires specialized expertise and meticulous execution to ensure the integrity and durability of that submerged structure.
Absolutely. Now, let's shift our attention to a type of concrete where aesthetics take center stage.
Yeah.
Architectural concrete.
I've seen some stunning buildings with those exposed concrete surfaces that have a beautiful, almost sculptural quality. I imagine that's architectural concrete.
You're exactly right. Architectural concrete is designed to be exposed as a finished surface, showcasing its texture, its color, and its form. It's often used in buildings, bridges, and other structures where visual appeal is paramount.
Yeah.
The handbook explains the key factors in achieving high quality architectural concrete, including careful formwork selection, precise placement techniques, and meticulous surface finishing. It also highlights the use of admixtures, pigments, and special aggregates to enhance the color, the texture, and the durability of architectural concrete.
It sounds like architectural concrete allows for incredible creativity in concrete construction.
Yeah.
Transforming it from a purely structural material to an aesthetically pleasing design element.
Precisely. Now, circling back to sustainability, let's explore concrete with recycled aggregate.
I'm always interested in learning about sustainable building practices.
So,
Using recycled materials in concrete seems like a great way to reduce waste and conserve resources.
you're absolutely right. Concrete with recycled aggregates incorporates crushed concrete or other recycled materials as a replacement for natural aggregates. This approach promotes sustainability by reducing the need for those virgin materials and minimizing waste. The handbook explains the considerations for using recycled aggregates in concrete, highlighting the importance of assessing their quality, their cleanliness, and potential impact on concrete properties. It also discusses the mix design adjustments that may be necessary when using recycled aggregates, emphasizing the need to ensure adequate strength, durability, and workability.
It's encouraging to see how the concrete industry is embracing sustainability by incorporating those recycled materials into its practices.
Indeed. Now let's shift our focus to energy efficiency and explore insulated concrete forms or ICFs.
ICFs sound intriguing. Can you tell us more about them?
Certainly, ICFs are prefabricated units made from insulating materials such as expanded polystyrene or polyurethane foam, which are used as formwork for concrete walls. The concrete is poured into the ICFs, creating a composite wall system that offers excellent thermal insulation and structural strength.
So it's like building a house with Lego blocks made of insulation and then filling them with concrete.
That's a great way to visualize it. The handbook explains the advantages of ICF construction, including reduced energy consumption, improved sound insulation, and faster construction times. It also provides guidance on the proper design, assembly, and installation of ICFs, ensuring that they meet the required structural and insulation performance standards.
ICF construction seems like a win-win situation. You get a strong and energy efficient building envelope all in one go.
Absolutely. Now let's move on to a type of concrete that's becoming increasingly popular for its environmental benefits: pervious concrete.
I've heard of pervious concrete, but I'm not quite sure how it works. Can you explain it?
Of course. Pervious concrete is a porous pavement material that allows water to infiltrate through it, reducing runoff and promoting groundwater recharge. It's often used in parking lots, sidewalks, and other paved areas where stormwater management is a concern.
So instead of water rushing off the pavement and into storm drains, it soaks into the ground.
Exactly. The handbook explains the unique mixed design and placement techniques for pervious concrete, emphasizing the importance of achieving that desired porosity and permeability. It also highlights the environmental benefits of pervious concrete, including reduced stormwater runoff, improved water quality, and reduced heat island effects.
Pervious concrete seems like a fantastic solution for creating more sustainable and environmentally friendly urban spaces.
It certainly is. Now let's shift gears again and discuss mass concrete, which is used in those massive structures like dams and foundations.
I imagine working with such large volumes of concrete presents some unique challenges.
You're absolutely right. Mass concrete refers to large volumes of concrete typically used in structures like dams, foundations, and retaining walls. It presents unique challenges due to the significant heat generated during the hydration process, which can lead to cracking and other problems. The handbook explains the special considerations for mass concrete mix design, including using low heat cements, temperature control measures, and careful placement techniques to minimize those thermal stresses. It also highlights the importance of monitoring the concrete's temperature during and after placement to ensure it cures properly and avoids that excessive heat buildup.
It sounds like mass concrete construction requires careful planning and execution to manage the challenges associated with those large volumes of concrete and the heat generated during hydration.
Indeed. Now let's move on to another type of concrete used in large-scale projects. Roller compacted concrete, or RCC.
I'm not familiar with RCC. Can you tell us more about it?
Certainly, RCC is a dry concrete mix placed and compacted using heavy rollers, similar to how asphalt pavement is constructed. It's often used for dams, pavements, and other applications where large volumes of concrete are needed, and a relatively rough surface finish is acceptable. And the handbook explains the unique mix design and placement techniques for RCC, emphasizing the importance of achieving that desired compaction and density. It also highlights the advantages of RCC, including its speed of construction, cost effectiveness, and durability.
It sounds like RCC is a practical and efficient solution for those large scale concrete projects where speed and efficiency are paramount.
Precisely. Now, let's turn our attention to high performance concrete, or HPC, a type of concrete that goes above and beyond in terms of its properties.
HPC sounds intriguing. What makes it so special?
HPC is a general term for concrete exhibiting superior properties compared to conventional concrete, such as higher strength, greater durability, and improved resistance to cracking and other forms of deterioration. It's often used in critical infrastructure such as bridges, tunnels, and high-rise buildings where long-term performance and resilience are essential.
So HPC is like the superhero of concrete,
Yeah.
Stronger, tougher, and more resilient.
That's a great analogy. The handbook explains the key principles of HPC mix design, including the use of high-quality materials, low water to cement ratios, and those advanced admixtures to achieve the desired performance characteristics. It also highlights the importance of quality control measures and rigorous testing to ensure that HPC meets those stringent performance requirements.
HPC sounds like a valuable tool for creating durable, resilient, and sustainable concrete structures that can withstand the test of time and the challenges of demanding environments.
Absolutely. Now, shifting gears from new construction to the maintenance of existing structures, let's talk about concrete repair.
I imagine that even the most durable concrete can eventually suffer damage or deterioration over time. What can be done to address those issues?
You're right. Even the best concrete can be affected by various factors. Over time, concrete repair involves addressing damage or deterioration in those existing concrete structures, restoring their structural integrity and extending their lifespan. The handbook provides a comprehensive overview of concrete repair principles and techniques, covering a wide range of issues, including cracking, spalling, corrosion, and chemical attack. It explains the importance of proper diagnosis of the underlying causes of concrete damage, selection of appropriate repair materials, and meticulous execution of repair procedures to ensure long-term success.
Concrete repair sounds like a crucial aspect of maintaining the safety and functionality of our built environment, extending the lifespan of existing structures and minimizing the need for those costly replacements.
Indeed. Now, let's explore a related area, concrete protection.
Concrete protection sounds like a proactive approach to ensuring the long-term durability of concrete structures.
Mm-hmm.
What does it involve?
You're exactly right. Concrete protection involves applying coatings or other treatments to concrete surfaces to enhance their durability and resistance to various forms of deterioration. The handbook provides guidance on selecting and applying appropriate protective coatings, considering factors like the type of concrete, the environment, and the specific threats the concrete is exposed to. It covers a range of protective treatments, including waterproofing coatings, anti-carbonation coatings, corrosion inhibitors, and chemical-resistant coatings.
It sounds like concrete protection is a valuable strategy for extending the lifespan of concrete structures, particularly in harsh environments or where the concrete is exposed to aggressive chemicals or other damaging agents.
Absolutely. Now let's discuss a specialized type of concrete construction, shotcrete.
I've heard of shotcrete, but I'm not sure what it is. Can you enlighten me?
Of course. Shotcrete, also known as sprayed concrete, involves projecting concrete onto a surface at high velocity using a hose and a nozzle. This method is often used for applications like tunnel linings, slope stabilization, and swimming pools where conventional formwork is difficult or impractical. The handbook explains the different shotcrete processes, including dry mix and wet mix methods, highlighting the advantages and limitations of each approach. It also provides guidance on selecting the appropriate shotcrete equipment, nozzle techniques, and mix designs to achieve the desired results.
Shotcrete seems like a very versatile and efficient concrete construction technique, enabling the placement of concrete in challenging locations and achieving complex shapes and contours.
You're exactly right. Now let's revisit self-consolidating concrete, or SCC, which we discussed earlier.
I remember you mentioned that SCC flows effortlessly into place without needing vibration. It sounds like a real game changer for concrete construction.
It certainly is. SCC is a highly flowable concrete mix designed to flow into place under its own weight without the need for vibration. This innovative concrete technology offers numerous advantages, including faster construction times, reduced labor costs, and improved concrete quality. The handbook explains the unique mix design principles for SCC, emphasizing the importance of achieving a high degree of stability to prevent segregation and ensure homogeneous concrete structure. It also discusses the various testing methods used to evaluate the flowability and stability of SCC, ensuring that it meets performance requirements.
SCC has revolutionized concrete construction in many ways, making it easier, faster, and more efficient to place high quality concrete in complex forms and congested reinforcement. I'm eager to see how this technology continues to evolve and shape the future of concrete construction.
Me too. Now let's delve into another type of concrete that enhances its properties: fiber reinforced concrete, or FRC.
We discussed fiber reinforced concrete earlier, but I'm always interested in learning more about how fibers can improve concrete's performance.
Certainly. As a reminder, FRC incorporates fibers into the concrete mix to enhance its properties, including tensile, strength, ductility, and toughness. The fibers can be made from various materials such as steel, glass, or synthetic polymers, each offering unique benefits. The handbook explains the different types of fibers and their specific applications, highlighting how they improve the concrete's resistance to cracking, impact, and abrasion. It also discusses the mixed design considerations for FRC, emphasizing the importance of achieving proper fiber dispersion and orientation to maximize their effectiveness.
It's amazing how the addition of these tiny fibers can significantly impact the concrete's overall performance and durability, making it suitable for such a wide range of applications.
Indeed. Now let's revisit high strength concrete, or HSC, which we touched upon earlier.
I remember that HSC boasts incredible compressive strength. What are some of the key factors that contribute to its exceptional strength?
As a refresher, HSC is characterized by its exceptional compressive strength, typically exceeding 60 MPa or 8,700 psi. It's often used in high-rise buildings, bridges, and other structures that demand that exceptional load-bearing capacity. Achieving HSC involves a combination of factors, including a low water-to-cement ratio, using high-strength aggregates and careful curing practices. The handbook also highlights the role of admixtures such as superplasticizers and silica fume in enhancing the strength and durability of HSC.
It's fascinating how the careful selection of materials and precise control of the mix design and curing process can lead to such remarkable increases in concrete strength.
Absolutely. Now let's revisit lightweight concrete, which we discussed earlier.
I remember learning about how lightweight aggregates are used to reduce the density of concrete. What are some of the key benefits of using lightweight concrete?
As we discussed before, lightweight concrete is characterized by its reduced density compared to conventional concrete, typically achieved through the use of lightweight aggregates. It's often used for applications where weight reduction is a primary concern, such as roof decks, floors, and precast concrete elements. The handbook explains the different types of lightweight aggregates and their properties, highlighting their benefits for reducing dead loads in structures, improving thermal insulation, and enhancing fire resistance. It also discusses the mix, design considerations for lightweight concrete, emphasizing the need to balance strength, durability, and density to meet the specific project requirements.
It's impressive how lightweight concrete can provide both structural and functional advantages, making it a versatile choice for various construction needs.
It certainly is. Now, let's revisit underwater concrete, which we touched upon earlier.
I recall that underwater concrete construction presents unique challenges due to the fluid environment. Can you remind me of some of the key considerations for this type of construction?
Of course. Underwater concrete is used for structures that are cast below the waterline, such as bridge piers, foundations, and marine structures. It presents unique challenges due to the fluid environment and the need to prevent washout and segregation during placement. The handbook explains the special considerations for underwater concrete mix design, including the use of high cement contents, anti-washout admixtures, and careful placement techniques. It also highlights the importance of monitoring the concrete's properties and ensuring adequate curing in an underwater environment.
Underwater concrete construction sounds incredibly complex and demanding, requiring a high level of expertise to ensure a successful outcome.
You're absolutely right. Now, let's circle back to architectural concrete, which we discussed earlier.
I remember learning about how architectural concrete is designed to be exposed as a finished surface, showcasing its aesthetic qualities. What are some of the key techniques used to achieve the desired aesthetic effects in architectural concrete?
Architectural concrete is often used in buildings, bridges, and other structures where visual appeal is paramount. The handbook explains the key factors in achieving high-quality architectural concrete, including careful formwork selection, precise placement techniques, and meticulous surface finishing. It also highlights the use of admixtures, pigments, and special aggregates to enhance the color, the texture, and the durability of architectural concrete.
It's fascinating how the creative use of formwork placement techniques and surface treatments can transform concrete into a visually stunning and expressive design element.
Indeed. Now, let's revisit concrete with recycled aggregates, which we discussed earlier.
I recall learning about how using recycled aggregates in concrete promotes sustainability by reducing the need for virgin materials. What are some of the key considerations for using recycled aggregates in concrete?
Concrete with recycled aggregates incorporates crushed concrete or other recycled materials as a replacement for natural aggregates. This approach promotes sustainability by reducing the need for virgin materials and minimizing waste. The handbook explains the considerations for using recycled aggregates in concrete, highlighting the importance of assessing their quality, their cleanliness, and potential impact on concrete properties. It also discusses the mixed design adjustments that may be necessary when using recycled aggregates, emphasizing the need to ensure adequate strength, durability, and workability.
It's encouraging to see how the concrete industry is finding innovative ways to incorporate sustainable practices into its operations while still maintaining the high performance and durability of concrete structures.
Absolutely. Now, let's revisit insulated concrete forms, or ICFs, which we discussed earlier.
Right. I remember learning about how ICFs combine insulation and structural strength in a single system. Can you remind me of some of the key benefits of using ICFs for construction?
Of course. ICFs are prefabricated units made from from insulating materials such as expanded polystyrene or polyurethane foam, which are used as formwork for concrete walls. The concrete is poured into the ICFs, creating a composite wall system that offers excellent thermal insulation and structural strength. The handbook explains the advantages of ICF construction,
Right.
including reduced energy consumption, improved sound insulation, and faster construction times. It also provides guidance on the proper design, assembly, and installation of ICFs, ensuring that they meet the required structural and insulation performance standards.
ICF construction seems like a very efficient and effective approach to building energy efficient and sustainable structures.
It certainly is. Now let's revisit pervious concrete, which we discussed earlier.
I recall that pervious concrete is a porous pavement material that allows water to infiltrate through it, reducing runoff and promoting groundwater recharge. What are some of the key environmental benefits of using pervious concrete?
Pervious concrete is often used in parking lots, sidewalks, and other paved areas where stormwater management is a concern. The handbook explains the unique mixed design and placement techniques for pervious concrete, emphasizing the importance of achieving the desired porosity and permeability. It also highlights the environmental benefits of pervious concrete, including reduced stormwater runoff, improved water quality, and reduced heat island effects.
Pervious concrete seems like a great way to integrate sustainable practices into our urban landscapes, helping to manage stormwater and mitigate some of the negative environmental impacts of paved surfaces.
Absolutely. Now let's revisit mass concrete, which we discussed earlier.
I remember learning about the challenges associated with mass concrete construction due to the heat generated during the hydration process. Can you remind me of some of the key considerations for managing this heat and preventing problems in mass concrete structures?
Mass concrete refers to large volumes of concrete typically used in structures like dams, foundations, and retaining walls. It presents unique challenges due to the significant heat generated during the hydration process, which can lead to cracking and other problems. The handbook explains the special considerations for mass concrete mix design, including using low heat, cements, temperature control measures, and careful placement techniques to minimize those thermal stresses. It also highlights the importance of monitoring the concrete's temperature during and after placement to ensure it cures properly and avoids excessive heat buildup.
Mass concrete construction sounds like a very specialized area of concrete technology that requires a deep understanding of the material's behavior and the ability to anticipate and manage potential problems.
You're absolutely right. Now let's revisit roller compacted concrete, or RCC, which we discussed earlier.
I recall that RCC is a dry concrete mix placed and compacted using heavy rollers. What are some of the key advantages of using RCC for construction?
RCC is often used for dams, pavements, and other applications where large volumes of concrete are needed and a relatively rough surface finish is acceptable. The handbook explains the unique mixed design and placement techniques for RCC, emphasizing the importance of achieving the desired compaction and density. It also highlights the advantages of RCC, including its speed of construction, cost effectiveness, and durability.
RCC seems like a very practical and efficient solution for large-scale concrete projects where speed and cost-effectiveness are important considerations.
Precisely. Now, let's revisit high-performance concrete, or HPC, which we discussed earlier.
I remember that HPC exhibits superior properties compared to conventional concrete. Can you remind me of some of the key principles of HPC mixed design and how they contribute to its exceptional performance?
Of course. HPC is a general term for concrete exhibiting superior properties compared to conventional concrete, such as higher strength, greater durability, and improved resistance to cracking and other forms of deterioration. It's often used in critical infrastructure such as bridges, tunnels, and high-rise buildings where long-term performance and resilience are essential. The handbook explains the key principles of HPC mixed design, including the use of high-quality materials materials low water to cement ratios and those advanced admixtures to achieve the desired performance characteristics. It also highlights the importance of quality control measures and rigorous testing to ensure that HPC meets those stringent performance requirements.
It sounds like HPC pushes the boundaries of concrete technology, enabling the construction of more durable, resilient, and sustainable structures.
Absolutely. Now, shifting our focus to another important aspect of concrete construction, joints.
Joints are often overlooked, but I imagine they play a crucial role in the performance and durability of concrete structures. Can you tell me more about them?
You're right. Joints are essential for allowing even concrete structures to move and breathe without cracking. Joints are intentional breaks or gaps introduced into concrete structures to accommodate movement and prevent cracking. The handbook provides a comprehensive overview of different types of joints, including construction joints, expansion joints, and control joints. Construction joints are created when concreting is stopped and then resumed at a later time, while expansion joints are designed to allow for expansion and contraction of the concrete due to temperature changes. Control joints are intentionally weakened sections that encourage cracking to occur in a controlled manner, preventing random cracking that could compromise the structure's integrity. The handbook explains the proper design. The handbook explains the proper design and placement of joints, emphasizing the importance of using appropriate joint sealants and water stops to prevent water ingress and maintain that structural integrity of the concrete.
Joints seem like a small detail, but they clearly have a significant impact on the long-term performance and durability of concrete structures.
Absolutely. Now let's turn our attention back to formwork, which provides that temporary mold for shaping concrete.
I remember learning about the importance of selecting appropriate formwork materials and using release agents to prevent the concrete from sticking.
What are some of the other key considerations for formwork design and construction? Formwork plays a crucial role in achieving that desired shape dimensions and surface finish of concrete structures. The handbook emphasizes the importance of selecting appropriate formwork materials, considering factors like the type of concrete, the desired finish, and the structural loads. It also provides guidance on the design, construction, and handling of formwork, ensuring that it can withstand the pressure of fresh concrete and produce that desired shape and dimensions of the structure. The handbook also discusses the use of release agents, which prevent the concrete from sticking to the formwork, allowing for easy removal and achieving a smooth finish. It explains the different types of release agents and their suitability for various formwork materials and concrete types, highlighting the importance of applying them evenly and at the correct rate to avoid defects in the concrete surface. The handbook also emphasizes the importance of proper formwork removal techniques to prevent damage to the concrete and ensure a clean, aesthetically pleasing finish.
It sounds like there's a lot more to formwork than meets the eye, requiring careful planning and execution to ensure a successful outcome.
You're absolutely right. Now let's revisit curing, which is a critical step in concrete production.
I remember learning about how proper curing is essential for maximizing concrete strength and durability. Can you remind me of some of the different curing methods and why it's so important to protect fresh concrete from premature drying and temperature extremes?
Curing involves maintaining adequate moisture and temperature for fresh concrete, allowing for optimal hydration and strength development. The handbook explains the different curing methods, such as covering the concrete with plastic sheeting, applying curing compounds, or misting with water, highlighting the importance of selecting the most appropriate method for the specific project conditions. It also provides guidance on the duration of curing, emphasizing that the concrete needs to be protected from premature drying and temperature extremes, as these can lead to cracking, reduced strength, and diminished durability. Proper curing is essential for maximizing the strength and durability of concrete, ensuring it can withstand the test of time and perform as intended.
It's remarkable how much attention to detail is required at every stage of concrete production, from selecting the right materials to the final curing process.
Absolutely. And the Sika Concrete Handbook does a fantastic job highlighting the key considerations and best practices for achieving high-quality, durable concrete.
Well, it seems we've covered a lot of ground today, exploring the fascinating world of concrete and the wealth of knowledge contained within the Sika Concrete Handbook. From its humble components to its diverse applications and specialized types, concrete is truly a remarkable material that shapes our built environment in countless ways.
It has been a pleasure diving into the intricacies of concrete with you today. The Sika Concrete Handbook serves as an invaluable resource for anyone involved in concrete construction, providing a wealth of knowledge and practical guidance.
From understanding the fundamental principles of concrete technology to exploring the nuances of specialized concrete types and construction techniques, this handbook equips us with the tools to create durable, resilient, and sustainable concrete structures. Whether you're a seasoned engineer or just beginning your journey in the world of concrete, the Sika Concrete Handbook is a valuable companion guiding you toward best practices and helping you navigate the complexities of this remarkable material. So as we conclude our deep dive into the world of concrete, remember that this material is far more than just a simple mixture. It is a testament to human ingenuity, a material that has shaped our civilization and continues to evolve to meet the challenges of the future.
Keep exploring, keep learning, and let this newfound knowledge empower you to create a built environment that is both strong and sustainable.
Thank you for joining us on this journey through the world of concrete.